Welcome to Integration by Ports. This is a calculus technique for integration. It's a very important technique. Sometimes the uh, integrals that we take are not really practical to do by any other method. So integration by ports involves integrating the product derivative and parts of a product derivative. So let's recall that the derivative of a product is the first function times the derivative of the second, plus the second function times the derivative of the first. It's always very important to understand where and why what we're doing comes from and works. So we're going to rearrange the terms of the original equation, and we're going to write f times the derivative of g with respect to x is the derivative of the product minus g times the derivative of f with respect to x. So that's just simply subtracting this term, g of x, df of x, dx from both sides. Next, we're going to integrate, and the integration of the difference is the difference of the integrals. So we're going to have the integral of f of x times the derivative of g of x. Then there's the differential equals the derivative of the product times the differential. Then there's g of x, the derivative of f of x times the differential. So we've integrated through, and we'll use this when we're trying to find this integral. So the technique is to let u be f of x, just like we would in substitution. Only the tricky part is we can't find du here. So we can find dv, derivative of another function, as the derivative of g of x with respect to x dx. And so then we would need v, which would come from here. That would be g of x, and du, which is the derivative of f of x dx. So we have our substitutions set up, and we'll make the substitutions. We'll realize that the integral of d product uv dx times the differential is simply uv plus a constant of integration. And we're going to just hold off on that constant of integration because there'll be another one coming from here and one coming from here. And we're going to add all the product, all those constants of integration together in the end and make one general constant of integration. So without belaboring the constant, the integral of u dv equals uv minus integral v du. If it looks like two substitutions going on simultaneously, it's because it absolutely is. So we'll work an example. We'll go through the example of finding the integral of x e to the x dx. Now, here's the difficult part. There's nothing that tells us what to choose for u. There's nothing to tell us what to choose for v. And it's by trial and error. And the more experience you have, and the more you can see derivatives of functions and whether they'll help and so on, the better you will become with efficiency at the technique. So we're going to let u, in this case, be x. Then du would simply be dx. Now, over here, we have the integral of u dv. So dv is going to come from here. So dv is e to the x dx. This is the derivative of something times dx. And so we're going to work our way back and find v. If this is the derivative of something, its antiderivative is e to the x. So we finally have all four parts. The u, the du, the dv, and the v. Now let's see if this does any good. Sometimes you do all this work and you find out you can't integrate this anyhow. So the integral u dv is ub minus integral v du. And that gives us the integral of x e to the x dx. The integral we want is x e to the x minus the integral of e to the x dx. Do we know what the integral of e to the x dx is? Well, yes. E to the x is its own derivative and its own integral. So now we know that we can just replace this integral with e to the x. And so the integral of x e to the x dx equals the product x sums e to the x minus, get out of this integration, e to the x plus c. Well, integration by parts is possible for definite integrals. The term uv would need to be evaluated for the limits of integration as well as the two integrals, since it comes from an integral. Unlike the substitution technique, all expressions must be in terms of the original variable before evaluating with the limits of integration. In the substitution technique, we can change the limits of integration from x to u and plug them in, or we can substitute back an expression for x and use the x values. Here we don't have a choice. We got to go back to the x values because we have two substitutions going on. Note that integration by parts may result in an expression on the right that also requires integration by parts. Sometimes we have to sort of step through the process. And finally, another possibility is that the integration on the right sometimes produces a multiple of the integral on the right. Sometimes is a multiple of the integral on the left, in which case we would collect algebraically the integral expression in one place and take care of whatever coefficient we might have had. Well, I would appreciate if any of you would like to see our other videos to hit the subscribe button. We do appreciate people subscribing to the channel, and there are many others, and not just in calculus. And we also have physics and other math topics. So thank you.